All right, everybody say hi, Lily.
Hola, Lily.
Again for the second time because my first recording just stopped. We're on example 3 for section 5.3, and we started writing down some information that we need. So we said 5,000 was our principal, 7% we read as 0.07, that's our interest rate. Compounded daily, what does daily mean?
The time. Or
Compounded daily.
annually.
And that means N is how many? 365. We're compounding every single day for 365 days. And that's what our N is. Okay, other information? When will the investment be worth 6,800? So what are we solving for?
The thing.
What variable tells me when?
Egg.
What variable tells me when?
A T.
T. We're trying to solve for T, right? What is A then?
68,000.
That's the 6,800, right? Okay. So 6,800 equals 5,000 times 1 plus 0.07 over 365 to the 365 t power. So we're trying to figure out when 5,000 will turn into 6,800. Okay, so we're going to plug some random numbers in for t and see what we get. Okay, so anybody got it narrowed down kind of? And we'll just attack. At the end of this chapter, we'll start to learn shortcuts for unwinding this equation, and then we'll be able to solve for t exactly. But as of right now, we don't know how to do that yet, so we're just going to plug random numbers in for now. Okay? But yes, we will get to a point where we don't have to do it this way anymore. Okay? Plugging random numbers in. Where are you guys starting at? Like, do you start with 10 maybe, or 7%? That's a pretty high percentage. I would maybe start at like 8 years or something. I don't know. Plug that whole formula in.
Wait, why is it 5,000 underlined again?
It's not. I just underlined it for no reason. I was just saying, when does 5,000 turn into 6,800? That's why I have it underlined. It's not really significant. Okay. I don't know. Oh. Does anybody got a number to start with? Any number that's close?
I started with 8.
You started with 8?
It's like you're gonna.
What was 8? What was 8?
875 for T.
Wait, what?
I think I did it wrong.
Yeah, I don't think you typed it in right.
Oh wait, maybe I put 500. Oh, I put 500.
That's the problem.
Okay.
That's the whole problem. What?
4.5. I'm sorry.
4.5?
Is 6851.
Okay, 4.5 is 6851. Okay. Exactly, 6851, something like that.
4.4 is 6803.
Oh, 4.4 is 6803. So we're getting pretty close there.
Ew.
Do we want to try to get closer? We could say 4.4. If we want to. We could keep going. Although too, right?
Ew. Okay. Well, what's 4.3?
Or 4.39 or 4.41. That's where I would start next, right? 4.41 or 4.39?
4.394 is 6,800.449.
394, you said?
Yeah,
4.394 was 6,000 what?
800.4494.
So 4.5.
Yeah.
That is pretty darn close. Let's go with that. So, what does that mean?
It takes about 4.5.
4.394 years. Okay. Now, do we have to add that on to a certain year?
No.
No, because they didn't tell me what year 0 was. It's just saying if I invest it now at this, how many years will it take? 4.394 years. Okay? Make sense? Okay, now, which one gives me the most money? Compounding once per year, 4 times a year, which would be quarterly. Monthly would be 12 times a year. Daily would be $365. Why?
Because
Do you remember?
You're getting an income every day, not.
So you're still only getting, like, for this problem, you're still only getting 6.4% interest all the way through for the entire year. But when they compound it daily, they're separating that 6.4% for the entire year, and they're taking that percentage of your new total each time. So it's giving you just pennies and dollars more than what it was before. Okay. So as you compound daily versus monthly, quarterly, annually, daily is going to give you the most money. Now, what's the maximum number of times you can compound?
Well, I don't know.
Like, they're compounding daily. Could you compound every hour? Could you compound every minute? Could you compound every second?
Yeah, it says right here.
Could you compound every millisecond? Because milliseconds is going to give you more money than hours, right? The more often you compound, the more money you get, right? So can we compound every millisecond or every tenth of a millisecond, which is going to give me even more money than that? Like, where do I stop at? Okay, so the deal is the more times I compound, so annually versus semi-annually. Semi-annually is twice a year. That's going to give me more money than annually. But quarterly is going to give me even more money. Monthly is going to give me even more money. Daily is going to give me even more money, more money, more money, more money. So the further I go down this list and the more times I'm compounding, the more money I'm going to get. So at what point do I stop and say that's enough?
Annually.
The deal is, as we're going through here and we're computing that compound interest formula, there is a number that each one of these guys in parentheses approaches. Okay? As I go further and further and further down this list, that number gets closer and closer and closer to a magic number, and it is called E. So, I don't have to compound every minute, every second, every millisecond, because I know that the more often I compound, the closer that value is going to get to the value of E, which is 2.7182818, and then I can't remember anything beyond that, right? It was at the top of this, was that at the top of this sheet? No, at the top of section 5.2, we learned what E was, okay? E was that number in your calculator. So we no longer have to compound every minute or every second or monthly or whatever else. We can just use E, and E covers all of our bases, okay? And instead of using the compound interest formula, we use something that's called continuous compounding. Okay? So we're continually compounding every millisecond, every fraction of a millisecond, we're compounding that many times, and we are using the number of E. Okay? And the formula that we use is a really easy formula. Instead of using compound interest, where we're compounding every month or every quarter or whatever, or daily, we use something called PERT. Okay? This is the formula for continuous compounding. It's probably on the next page. Yep, right here it is. A equals PE to the RT power. The RT is the exponent. But we no longer have the stuff in parentheses, because all of that stuff that's in the parentheses is going to get closer and closer to E the more times I compound per year. Okay? So we replace that with E, and when we're continually compounding, we use E instead of the stuff that was in parentheses. Okay? I don't know. These are, let's see. Today is, this is fourth period. 1:40 is when we get out. So we've got like 25 minutes left, maybe something like that. Okay? So PERT, suppose you invest $1 for 1 year at 100% annual interest, compounded n times per year. It says find the maximum value of the investment. So this is going through and it's saying if you compounded annually, you would get $2. If you compounded semi-annually, you would get $2.25. I'm investing $1, right? You would get $2, you would get $2.25, you would get $2.44, you get $2.61, $2.71, and then it approaches that number E the more and more and more times I compound. Okay? So instead of using compound interest where we're compounding every second, every minute, whatever, we're going to use that continuous compounding. Okay? So this just kind of illustrates where that letter E comes from, or that number E, I guess, comes from. Okay? Let's go to a problem on the next page.
What do you put E?
What? Right here, E. I think they have, I don't know. E equals that number. It's on your section 5.2 notes.
Doesn't E already like on your calculator?
Yeah, there is a button for E on your calculator, so you don't necessarily have to remember what it is. 2.7-ish. That's what E is. Okay. All right. Good.
Yeah.
Okay, let's go down and do a problem with this. So all you have to remember is PERT. Okay. If you invest 4,000, what's 4,000 going for?
Are you supposed to remember example 4?
No, example 4 was just illustrating this whole table, so they've done it for us. Okay. So 4,000 is my investment, so that goes in for what? P. The interest rate is 5%, so we're going to put that in for R, but we're going to say R equals 0.05. Okay. Compounded continuously, so that's how we know we are using PERT when it says compounded continuously. That's my PERT equation. How much is in the account at the end of 3 years? What's 3? 3 is T. Okay, and that's all the information we need. We're solving for what? We're solving for A, right? We're solving for A. So 4,000 times E to the 0.05 times 3. Okay, and we just need to plug that in and solve for A. Just type in the whole thing. 647.34. There you go. Does that seem like an appropriate amount of money?
Yep.
Yeah, probably. 5% interest for 3 years. We're making about $647 interest. Sounds good. Okay, so when you're continuous compounding, use PERT. If you're compounding annually, compounding monthly, whatever, you're going to use the other compound equation. Okay. All right. Next, population growth. They give me a formula for population growth. Exponential growth is written as this function right here, where P, what's P going to stand for? The principal, okay? For population growth, did we decide it was P-A-L or E-L? Or L-E? A-L, whatever, doesn't really, I don't know if it really matters. Is it?
I think it's actually L-E because principal is your like.
Yeah, your principal.
Yeah.
It's like
Yeah.
less or more.
Because they're your pal. I remember that.
Yeah.
Yeah. But principal is like a rule, isn't it?
And this is kind of a rule.
Yeah.
Okay, whatever. Principal. A, what's A going to be your stuff? What is A?
You forgot the N in principal.
Oh, principal. C-I-P-L-E. There you go. There we are. I can't spell. A, what's A going to be? A is going to be your growth rate. So growth rate. Okay, so if I'm growing, let's say 20% per year, my growth rate is actually going to be like 1.2 because it's 120%. Okay, we'll talk about that here in a second. Here's another way of writing this because you're going to add your growth rate to that, like you're adding your R. X. What's X going to be?
That's your years.
Usually your time. Okay, but for some reason they put it as X this time, whatever. So that's usually your time. Usually we'll write it as T instead of X. Okay. All right, so let's figure out what stuff goes in here. The world population in 1950 was about 2.5 million. Okay, so I'm going to go 1950 is like our year 0, and we're starting at 2.5 billion. So I'm going to write that there just so that we know. Yeah, X equals 0 corresponds to 1950. Okay, has been increasing at approximately 1.85% per year. Write the function that gives the world population. So R is going to be 1.85%. Write the function that gives the world population in year X. Okay, so f of x equals, we have PA to the x power, and we've got to put some information in there, all right? So P is 2.5, sure. Okay, now we have to figure out what A is. So if I'm growing 1.85% per year, okay, this as a decimal is 0.0185, right? Okay, but 1.85 is what I'm growing. So if I look down here and I'm trying to figure out what A is, I add that to 1.
So it's going to be 1.0.
1.0185. That's going to be my A, and I'm going to put him in parentheses. 1.0185. Do you guys know why we add that 1 in there?
No.
So there's no decimal.
Because if we're growing, that means we're increasing. We're 100% plus the 1.85% on top of that. And 100% is 1 plus the 1.85%, right? So it's 1 on 1.85. If I would just leave this as 0.0185, what would happen to my population? It's going to shrink every time, right? Because it's a number less than 1. If it's a number greater than 1, it's got to grow, right? So we have to add the 1 on there so it grows.
So
Because
every
it's
time
100%.
each number that is greater than 1, add that 1.
Yes, right. So if I'm increasing that percent, I'm going to add that to 1. What happens if you're like depreciating like
You don't add
2%?
subtract 1.
You would subtract it from 1, right? Okay. So if I'm depreciating 20% every year, you would put in 80% because I'm going down 20% per year. So it's 80% is the number that you're going to use. Okay. We'll have a depreciation one down here below. Okay. And that's what f of x is. Okay. Or if you want to call it a, you can call it a. I don't care. Is that what we were trying to do?
Yes.
Write the function that gives the world population in year x, where x equals 0 corresponds to 1950. This is my formula. Okay. Now, what units is this thing in?
Billion.
In billions. Okay. If you wanted it set up to be in millions, you could do 2500, because that would be 2.5 billion is 200 or 2,500 million, right? Does that make sense?
Yeah.
So it depends on how you want it set up. Technically, either of these are the correct answer, but this one is in billions. This one's in millions. Okay? So there's more, kind of more than one right answer here. Okay? Make sense? All right. They were just having us write the equation for that. All right. Example 7. Bacteria growth. At the beginning of an experiment, a culture contains 1,000 bacteria. What's that?
That's P or P.
That's P. 5 hours later. What's that?
Time.
Time. Okay, and let's put 5 hours just so that we know what our equation or what our units are in. There are 7,600 bacteria. So what's 7,600?
That's the end.
That's the end amount, okay? Which we usually call it A. Can we switch this instead of f of x? Can we call it A instead? So after amount is 7,600. Okay? Assuming that the bacteria grow exponentially, how many bacteria are there after 24 hours? So that's time again. But we've got to figure out what our growth rate is. They don't give us our growth rate.
We gotta plug stuff in to find it.
Right, so we got to plug stuff in to find what our growth rate is, and then we've got to plug 24 hours back in to figure out what our new amount is. Okay, so let's figure out where we put all our stuff in here. 760 or 7,600, right? 1,000 times 1 plus our rate to the 5th power. Okay, and we've got to figure out what our interest rate is. So how long do you think it's going to take? How many hours do you think it's going to? No. What percent is it growing at? 4.25. 4.25.
Yep.
Are you? Did you cheat or are you just guessing? You're just guessing. I think it's higher than that.
I think so too.
I think it's gonna be like huge. Nah, I don't know. Maybe not. Okay, we know that R is going to be a decimal number, right? Like 0.0 something. Okay. So plug in some numbers and see what we get. Then we got something close that they want to share to help narrow it down. Okay, we're just trying to pick numbers to plug in. Oh, wait a second. We don't have to guess. Can we just solve this thing?
Yeah, I was gonna say, can't you?
Because R is not an exponent. We could just solve this thing. What? How do we solve it?
You have to
Distribute the 5.
No, we can't distribute the 5.
Divide by 1.
We have to divide by 1,000. We can't distribute the 5 because really this means 1 plus R times 1 plus R times 1 plus R. So we'd have to FOIL it 5 times. But we're not going to do that. Divide by 1,000. What's 7,600 divided by 1,000? Move the decimal. 7.6 equals 1 plus R to the 5th power. Okay, how do you get rid of the 5th power?
Take the 5th
Take the fifth root, right. Take the fifth root. So what's the, that's going to be a really big decimal. What's the, not a big decimal, a really long decimal.
Is it supposed to be a 5?
The fifth root, yeah, that's a 5. It kind of looks like a 3.
And then 7.6?
Yep, the fifth root of 7.6. Do you guys remember how to type that into your calculator? Fifth root?
It's 1.50024-ish.
1.50024. Okay, equals 1 plus r. So what's my rate? What's my r?
It's just gonna be 2.5.
Subtract 1. 0.5. We'll just say 0.50. We'll just round it off as 0.50. So our interest rate is 50%. So it's like growing by half each year, right? So if we started with 10, it's growing by half of that, so it'll be 15 the next year, right? Okay, so our R is 50. Okay, now they don't want to know that. They don't care about that. They want to know what our after amount is if we're looking at 24 hours, right? Is our equation set up to be in hours?
Yes.
Yep, so we're just trying to solve for X. Oh, no, wait. We're trying to solve for A.
I can't see.
Bleh. There we go.
Zoom out a little bit.
Okay, so 1.5 to the 24th power times 1,000. What's our after amount? Somebody want to take a guess?
Wait, 1.3.
It's
No?
168341112.
1683411
2.
2.2.
Oh my gosh.
That's not what you got?
I guess mine was just more accurate. I just
Yeah, because you used 0.0 or
I just plugged in the
0.5000.
number that my calculator.
Right. Is it
So I
close?
got-
Is it close?
Well, I got 16,900,721.
900,000. Oh, not okay.
0.32.
16,900,000 what?
900,721.32.
I have the exact
721.32.
thing that I put in the exact equation.
So here's the difference between the two. They're both pretty accurate, but the difference is Allie used 1.5002. She used the whole big long decimal thing versus using 1.50. So it's just like using 100 decimal places out versus 2 decimal places, and it just changes that much. Okay. So which one's more accurate technically? Allie's. I'll take either one though. Right. So Allie just put in left that big long decimal number in her calculator is what she did. And technically you can't have 0.32 of a bacteria. I guess it's splitting maybe or something. I don't know. So almost 17 million bacteria. Ugh, gross.
That's fine.
You guys have seen like a piece of bread and then in one day it's like black. You guys seen that? Like if you have a moldy piece of bread, it like takes not very long. That's because bacteria like breed really fast. Not breed, but they expand really fast. Okay. Oh, what do we have left? 2 of them. 2 left. Okay, exponential decay. The only difference between exponential decay and exponential growth is this. If you want to write a formula down, you can do this. A equals P times 1 minus R to the X power. That's the only difference because you're subtracting. Your interest rate is what you're subtracting. So if you want a formula, here's the formula for exponential decay.
Okay.
Same as growth, but it's minus R instead of plus R. Okay? When tap water is filtered through a layer of charcoal and other purifying agents, 30% of the chemical impurities in the water are removed. What's 30%?
0.3.
0.3, that's my R. Okay? That's how much we're removing. If the water is filtered through a second purifying layer, 30% of the remaining impurities in the water are removed again. And then 30% again, and then 30% again, and then 30% again, right? Okay? How many layers are needed to ensure that 95% of the impurities are removed? This is confusing. 95% of the impurities are removed. Okay, so if we want to set this up into this formula right here, okay, we can kind of use this formula here. 95% is what we want to have left over, right? Okay, so A is going to be kind of like your 95%. If I start with, let's say I start with 100 gallons of water, right? How much do I want to be removed from that? Or what do I want my after amount to be? 5, right? 95% is removed. So if I start with 100, I'm going to have 5 left over. We're just making up these numbers. right? Because we can, right?
Yeah.
We can make up those numbers, okay? Now, we are taking the 30% and we're taking it out and taking it out and taking it out every time. So 1 minus 0.3, and then we need to figure out how many times we're doing that, which is going to tell me how many layers we have. So in this case, instead of this variable representing time, this variable is going to represent layers, the number of layers I have. Does that make sense?
Yeah.
That many times I'm doing it, right? It's kind of like every year, except it's talking about the layers that we have, okay? So if we want to simplify this, 5 equals 100 times 0.7 to the x power, and we're trying to figure out how many layers that will give me. So 100 is what we're starting with, okay? The reason why I started with 100 is because I can easily find what 95% less than 100 is, right? I can do that really easily. You could have started with 1,000 and done 50, right? Or you could have done like 2,000 and done 100, whatever that relationship is, as long as 95% is removed. Okay? All right, how do you want to solve for x?
100 times 0.7.
7 and then divide it.
Now, you can't take 100 times 0.7
Divide
until,
Divide by 100.
Take the root of x. Can you
Yeah.
do that?
this one we have to plug stuff in, because we don't know how to solve this yet. I wish we knew how to solve it yet, okay?
You can simplify till.
Now you could take 5 divided by 100 is 0.05 if you want to do that. So you get to say 0.05, right? If we divide by 100. 5 divided by 100 is 0.05. So you just need to plug in 0.7 to the x power and see when it becomes 0.05. Does that make sense?
Well, yeah, I guess.
So you could do it that way, I guess. So how many times do you have to take 0.7 times itself in order to get 0.05? Ish. I can tell you what the exact answer is.
Okay, do it then.
Okay, I will. Okay, fine.
Oh, 0.05?
Oh, I don't like this. Do you want to know where to start?
I'm pretty close. Don't
Oh, okay. If you keep plugging numbers in.
Are we gonna do this last one?
No, I think we're gonna stop. And we got it real close?
8.39 is close-ish.
Yep.
0.05.
8.39905 is the exact answer.
Oh,
I could keep going on more than that, but that's what he should be, right?
yeah, that's right.
We get out.
Okay, makes sense? Good? You guys don't know how to solve these yet by using algebra, but you will by the end of this chapter. You will, I promise. Okay?
Why wouldn't you should have just taught us
There's a bunch of, like, it's a process. It's not like, yeah.
It's not a one and
It's not like a one and done thing to do it, okay? All right, so I'm going to save radioactive decay, which is example 8. I'm going to save that for tomorrow, but what I want you to do is, yeah, technically it's example 9. Work through as many homework problems as you can. So any of them that involve radioactive decay, you can skip for now. Yep. Right there. Okay? So do all those homework problems. Any of the radioactive decay you can skip. Okay? We'll finish those tomorrow. Okay? Good? What did you say?
Example 7.
What?
Can we look at example 7? Wait.
Can you look at example 7?
What?
Oh, you need to go back to it. Okay? Example 7. Right there. There you go. Okay?